Nice. So welcome, everybody. Thank you for coming this evening. I know the skies are a bit dark, but hopefully you enjoyed the view before it came around. So before we get started, I kind of want to see how much you guys know about the data storage market. So global data storage has kept increasing over time. It's probably going to keep increasing for a very long time. So let's see if you can guess what the market size of it was in 2024. So who thinks the market size was 500 million US dollars? No? Okay. Let's go to 10 billion US dollars. Got one. 100 billion? A few more. 200 billion? 500 billion? Okay, you guys are all around the same spit. It was 218 billion in 2024. So, quite good to keep up to date with these topics and see how you can optimize your costs. So without further ado, welcome to the Meetup. This Meetup, we're basically going to be talking about real-time databases and how they're integrating with data lakes in order to reduce storage costs and improve data sharing. So for anybody in the AI world, you're going to need a lot of data to make it work correctly, so might as well try and make it as cheap as possible. So first of all, we want to give a really big thank you to the trade desk for providing the beautiful venue, the food and the drinks, and I'm going to give them some time to talk over their slide.
Hello, thank you everyone. So I'm gonna go quick. We are the trade desk. We are a DSP in the digital advertising space. We serve roughly 15 million QPS about ads opportunities that we get, that we bid on, and we help our clients reach bigger audiences, get better buying decisions, and inform the clients. And also we show the results of their campaigns. And that's specifically the part that Omar and I work on. So a big shout to Omar for organizing all of this. Thanks a lot, Omar. So we're a big part of the reporting stack. These are the open positions. If you're interested about having more questions, or if you're interested about the company at all, please don't hesitate reaching out. Thank you very much.
Thank you again for having us. So tonight we're going to have three speakers. So we're going to have Robert, who's here, who is the CEO at Altinity. We're going to have Olena, who is in the first row, who is a staff developer advocate at Confluent. And we're going to have Prachi, who is right at the back, who is a senior solutions architect at AWS. So between the talks, we'll have a 5 to 10 minute break in case you want to get some more food and drinks. But without further ado, I'm just going to introduce Robert. So Robert, CEO at Altinity. Altinity is an enterprise provider for ClickHouse data warehouses. He's got experience in at least 20 DBMS types. It's quite a lot. And he's had the Kubernetes bug at VMware in 2018. So AI needs a lot of data. We all know that. And he's going to tell us how you can make sure that it's fast, that you can have fast, cheap, and flexible queries that extend the life of real-time analytic applications. Let's give a very warm welcome to Robert.
Can you guys hear me? All right, cool. Yeah, the 20 databases, I got that number by not using some of them for very long. I think the world record for me was DB2, which was 1 day. It was enough to decide I really didn't like it. So I moved on. Let me go ahead and bring my slides up. And while I'm doing that, I want to give, once again, a huge shout out to the trade desk for organizing this. This is a wonderful venue. We will be back, for better or worse. All right, oops, wrong thing. I always get share and slideshow mixed up. Okay, so I'm going to be talking about building a foundation for AI with ClickHouse and Apache Iceberg. It's mostly slides, but I'm going to run 6 or 7 queries at the end that show some of the speed things I'm talking about. I've already been introduced. I will say that just from my background, the other relevant thing is I've been working with databases for a long time, about 40 years. I've been a programmer for 53 at this point. So I've seen a lot of stuff, and I think this transition that we're seeing in storage and storage combined with AI is probably the single most interesting thing I've dealt with in my whole career. It's really, really fun. It's kind of amazing we get paid to work on this stuff. So just a little bit about my company, mostly like why about this. We're a vendor for ClickHouse. We're actually a competitor of ClickHouse Cloud. How many people know ClickHouse in this crowd? All right, how about half of you? It used to be about 2, and a few years ago, it's really the word has gotten around. So we are a vendor for ClickHouse. We're very focused on open source ClickHouse. We run a cloud, manage it for people. We also do enterprise support. And we do a lot of stuff in the community. For example, if you use Kubernetes, in fact, I can see some of you in the crowd who are using the Kubernetes operator for ClickHouse. We wrote that. So that's what we do. And that's where a lot of the background comes here. And actually, storage is very, very interesting to us because it's extremely expensive for our customers, as you will find out. So in case you don't know what ClickHouse is, it's a really, at this point, really well-known analytic database. What we call a real-time analytic database is to give you back results, ideally in a second or less when you're showing user dashboards, maybe tens of milliseconds if you're showing, like if you have a service which is asking for information to add to the page while it's being rendered. It has a lot of the characteristics of MySQL. It doesn't share any code with it, but it understands SQL, runs anywhere, has an open source license, in this case Apache 2.0, and then it has a number of features that are in common with modern analytic databases, like columnar storage, very good parallel and vectorized execution, and huge scaling. We'll talk about that in a bit. And so it's become incredibly popular. It's about as popular as Spark, if you look at the number of stars. And what I want to do is explain a little bit about how many people know the difference between rows and columns and why that is so significant. Okay, so some of these, this is going to be old hat. I want to start with why is it that columnar storage and the storage organization is so important for a database like ClickHouse. This is a query that runs in ClickHouse. It could run in any database pretty much on the planet that understands SQL. It's using this famous on-time database. It's US Airlines, and we're looking for the airlines with the most cancellations in a year. Some of our airlines are not very good about that. But the key thing here is it had to scan 196 million rows, and it did it in 2/3 of a second. So this was a full table scan on 3 columns. The question is, how did it do that so fast? Well, let's look at the organization. The key thing about analytics storage today is that the data is stored in columns. So you can think of them as arrays. And so when we ask for 3 columns, these are in separate files, so that's all we read. If you use a database like Postgres, how many people use Postgres? MySQL? About this, it's like MySQL's still hanging in there. MySQL and Postgres organize things in rows. So if you have a query that asks for one thing out of the row, one column out of the row, it's going to read the entire row. That has a huge impact on performance of reads. It's very convenient for updates. That's one of the reasons why they do it. But we can illustrate this impact by just considering how much data we actually have to read when we're processing this query on something like MySQL versus ClickHouse. So these spheres represent the volume of data that you're reading. And that data set, if I had put it on MySQL and run the query, I would have read 61 gigabytes of data in a single thread. Now, if I put that data on ClickHouse by doing absolutely nothing but just creating a table and running it, I'm actually only going to read about 1.5% of the data, because that table that I'm reading from, in fact, has 109 columns, and I only read 3 of them. I have system tables which allow me to tell exactly how much of the data set that represents. It's a very small amount. So I'm already down by, close to, over 50 times less data to read. The second thing, though, is columnar storage, because it's an array with common types, it compresses extremely well. The actual amount of data that we read from storage was 17 megabytes. That's an astonishing reduction of data. So we're talking literally thousands of times less data. And then finally, ClickHouse, in this particular example, I was using 8 vCPUs. So assuming they're all fully utilized, and ClickHouse is very good at doing that, each of them would read 2 megs of data. This is the kind of thing, when you use MySQL and you use Postgres, people say never do a table scan. That's like, well, an index range scan is worse, but you don't want to do table scans. In ClickHouse, they're cheap. It's just brute force because the data is compressed and we have parallel, and we read as little of it as possible, and we do what little we have to read, we read it in parallel. So this is why columnar storage is so important. And ClickHouse grew up. It was based on columnar storage. This is the architecture of ClickHouse. It uses what's called a shared nothing design. Each of the ClickHouse servers contains disk that it manages. It contains the tables. There's built-in replication between them. You can add data on any of the servers. Put it in one replica table. It will find its way to other replicas. That process is managed by what's called ClickHouse Keeper or Zookeeper. That keeps a list of who owns which parts of data, and ClickHouse basically handles moving the parts around so that all the tables stay consistent. And over time, ClickHouse has become increasingly good at reading data on object storage, specifically MergeTree, that's the native file format, and then of late, Parquet files, plus other different types of things. But ClickHouse has become very fast at reading and writing Parquet. So how many people run systems where you store data in Parquet? Is that, okay, good. So it's a file format, an open file format that allows you, that can be read by a bunch of different libraries like Arrow, for example. Okay, so great. That got ClickHouse to be the most popular analytic database on the planet. But sometimes you can be a victim of your own success. We have a customer that currently loads about 20 petabytes of uncompressed data into ClickHouse clusters per day. It compresses down pretty well, so it's about half a petabyte. But that's a huge amount of data. When I first started working with ClickHouse 6 years ago, we'd be lucky if we'd see people with 100 terabytes. These are enormous volumes of data. And things like observability and LLMs are really driving this, but other things like security management, trading, there's probably traders in the crowd here, and crypto, you guys are also driving this as well. So that's led to a couple problems with the architecture. One is that because in the classic shared nothing architecture, you have block storage, which is then replicated automatically by the database. If you have 3 replicas, you have block storage, which is already kind of pricey, and you're going to replicate it 3 times, so it's 3 times kind of pricey. Compare that to object storage, and I'm picking S3 because we use that a lot. It's about 10 times more expensive. I mean, there are some other charges for S3, like API charges, but the at-rest storage is very, very expensive in these large systems. The other thing is that if you have these big systems that are also being queried, you have to provision a lot of capacity so that they won't fall down while they're simultaneously reading data into the database, replicating it, changing it, compacting it so that it's more efficient, and serving up queries. And so you end up over-provisioning. And this wastes resources as well. So you may waste, a half of your computer more just so that you have enough around when, like, you have a hot trading day or something's broken in a big system, like you're having an outage and you need to find out fast. You don't want the system to fall down right then. So there's a third thing that happens, which is that if you don't get that over-provisioning right, your systems become unstable exactly when
my day off.
What? Okay. All right. I think that was somebody on Zoom. Yeah, so anyway, you get instability. These are actually causing serious problems. And on top of that, there's AI. And there's a huge amount of uncertainty about what is going to happen with AI. How many people use AI development tools? All right, I want to hear what your favorites are. But there's a new one every day. But there are a couple of things that are very clear that are happening now. One is that AI systems are getting access to data through things like MCP. They're adding load because of inference. And these are often kind of lumpy workloads. And then over time, people want to train on this data as well. So these are additional workloads. And what these are basically doing is just increasing the load on databases that are already loaded from real-time query. So what do we do? Well, we had a pretty simple idea, which was to take open source ClickHouse, which does not have a notion of shared object storage, and use Iceberg for that purpose. How many people have heard of Iceberg? Oh, this is pretty good. So Iceberg basically takes database storage, detaches it from the database, and creates a protocol where anybody can connect to the storage and run queries on it. So you can have it underneath something like ClickHouse and run queries on it, but you can also write a Python program that uses PyIceberg, and it also talks to Iceberg. You can have Spark updating the data. You can have ClickHouse reading it. You can have Python reading it. They all read it simultaneously. So this is a really interesting development. And one of the things that is really key about Iceberg is that it's open. And in many ways, if you use Iceberg, you probably know that it's not a perfect specification, but it's open source. And as a result, there's a huge number of libraries that can read it. And and it's also proven in very large systems. It was originally invented at Netflix. And one of the things that it does is allows people to have very large tables, to update them safely, and then to share those tables across many, many applications. And it's open source. So we decided, okay, we're going to take Iceberg and we're going to make that into native storage for ClickHouse. And that's how we're going to solve this storage problem, because people can put a bunch of their data, their cold data can all go on this shared storage, and then they won't have so much on the block storage. So that should be pretty easy, right? ClickHouse has got a lot of people committing to it. But it turns out, and if you look at upstream ClickHouse, which is the ClickHouse from ClickHouse Incorporated, they are focused on integrating with Iceberg. And they've put in some amazing features. I've listed a few here. One is a very fast Parquet reader that I'll illustrate in a minute. But the thing is that when you're using a database when you're using a particular file type for storage, you have a different set of considerations. One of the first things we had to deal with was adding compute storage separation so that people could really share this and they could also scale their compute to deal with that compute scaling problem. And this goes all the way down to solving problems like compaction, making sure that the files are are automatically compacted so that they become efficient. So it's a completely different set of considerations, and this is basically what Altinity, the company, is working on. We call it Project Antalya, and it's all being done in open source. We have our own builds of ClickHouse. You can think of this as a branch of ClickHouse that has these capabilities. So some of the things that we added, the first thing that we did was we took ClickHouse, which has a relatively static model because each of the servers has attached storage, and we introduced something that we call swarm clusters. These are stateless ClickHouse clusters that register themselves automatically and are available to run scans on object storage, specifically on Parquet files. And what you can do is for any query, if you are going out to, for example, an Iceberg table or looking at S3 in general, all you have to do is add this setting, which can be set automatically in the background so that it does it without you doing anything. And what that says is when we're running a query, if it's on object storage, we're just going to delegate out to this swarm, and they are going to run the queries for us. So we'll be able to scale the amount of compute that we're using. So this is the beginning of really a solution for compute storage separation. I'm going to skip this slide, but it just shows some example. I'll show you examples in a minute that are real ones. This is how it works. So this was kind of fun to put together. Basically what we do is we have multiple ClickHouse clusters. And the way we were able to do this pretty easily because we wrote the Kubernetes operator. So we pretty much do everything, all of our stuff on Kubernetes. You can set this up on-prem. If you have racked hardware, it works there too. But in Kubernetes, we set up a ClickHouse cluster, and that's where people arrive to get their queries processed. You have the swarm clusters, and you can just scale them up and down. They can use spot instances. You can use different compute. And every time one starts, it registers itself in Keeper, which is where we maintain consensus, and then it becomes automatically discoverable by the rest of the ClickHouse instances. And then this swarm cluster is responsible for your reads on Iceberg. So that's basically how the scans work. Another thing we did was just, databases, what really makes them run fast is caches. It's memory. So, and this has been true for decades. It's particularly true with a database like ClickHouse, where the whole point is, hey, make things run really fast. So anything we touch, we want to avoid, if we have to read data and we have to read it more than a few times, we want to have it in memory. So we've done a lot of work on caches, and I'll just give you one example. If you list files in S3, which you have to do, there's a thing called S3 list objects. It's a very slow call, and you have to make multiple calls to enumerate the files. We put the results in a cache. This speeds up some queries almost miraculously. So using memory effectively is something we've been very focused on. And then another thing that we added was a catalog. So catalogs are kind of like, everybody I think in this room probably knows what a database is. If you're in MySQL or you're in ClickHouse or Postgres, well, Postgres it's a schema technically. It is a collection of tables. So Iceberg has this same notion. It's called a catalog. And so this is a service that you can go to and find out what your tables are and where they're located, where to find their metadata. So we added a lightweight catalog because we found in working in Iceberg, somewhat surprisingly, that there wasn't good tooling for catalogs. In other words, something that's very, very simple that would run anywhere from your laptop to a CI/CD pipeline to a large cluster. So we built one based on the open source Java libraries. So with that, we basically have the full architecture. So you have the swarm clusters, you have the catalogs, you've got native ClickHouse tables for stuff that you want to run fast. You can put it on shared object storage. At this point, you can start hooking up your applications to it, everything from Kafka to AI, batch reports, data science. They can all go, those guys can go in through the catalog and talk directly to shared object storage. Your real-time queries can continue to come through ClickHouse or any other queries that you just want them to run fast. So speaking of fast, how fast is it? Well, I think everybody knows in the database business, it takes 2 years to do anything. It takes 10 years to do it right. So you might intuitively think, hey, this must be really bad because it hasn't been out for very long. Here's just some this is not very conclusive performance data, but just some sample queries. It's a famous data set on New York taxis, has about 1.5 billion rows. Here's the queries are very simple scans. It's not run on particularly large hosts, but we're comparing against the native MergeTree format. And the key thing about this, does anybody notice something about this graph? The yellow and the red are native ClickHouse storage. The blue ones are various flavors of queries using our Antalya code on object storage. Anybody notice anything about these queries? The bars in the graph? They're all about the same. When we first started testing Parquet reads versus MergeTree, the difference in performance is anywhere from 10 to 100 times slower. It's gotten really good. So at this point, Parquet queries have become very, very fast. So basically, this is proof that you can build systems on this, and if there's a performance problem now, pretty good chance it'll be solved soon. The integrated Iceberg catalog, I'm going to skip over this in the interest of time so that you can hear about Confluent. This is the key thing here is that it can load data, and this was actually one of the reasons that we ended up writing our own catalog. I have a feeling that for people who, like the folks who wrote the Unity catalog, this was also in the back of their mind. Iceberg is very, very inefficient on loading data. The metadata files are bloated. It has a very clumsy commit protocol. If you own the catalog, you can sort of play games and make it run faster. We fell victim to this temptation, and the idea is that you can just take Parquet files with this. You can just point to the Parquet files and say, make a table. The ICE tool set that we wrote will just read the Parquet, create the schema, stick the files out in the table. So we use that for moving data around in bulk. Another benefit of writing this catalog was it enabled us to integrate with S3 table buckets. How many people here have heard of S3 table buckets? Okay, you're going to hear a lot more about them from Prachi in a minute. This is a really cool feature. I'll just say it is managed Iceberg in an S3 bucket that is specially optimized to run S3, and Prachi will fill in the rest. It's a great feature. But this catalog, it has, when we first tried to integrate with it, it turned out it required authentication that is not supported by ClickHouse. So what we did was, and it's this Oz SIG-v4 protocol, which ClickHouse works in Python, does not work inside of ClickHouse. So what we did was we just tweaked our catalog and made it proxy into these S3 table buckets. That's how we connected up S3 S3 table buckets in a matter of a couple weeks. So I think that's it. So looking ahead, one of the things that is really important to make this work is to be able to have tables that contain a mixture of the native merge tree, this very fast, quickly compacting data that you can, where you can insert data, see it come up, like in a few seconds, or be instantly queryable after insert, but also be able to see large amounts of cold data in Iceberg and have it look like the same table. This is often called tiered storage. We have a new table engine, which we just released in an experimental form on Friday. It's called a hybrid table. It basically tracks these as segments, and it has what's known as a watermark, which is used to distinguish who owns which segment owns which part of the data. So what this will allow us to do is extend ClickHouse so that you can now say, hey, after 30 days, move my data out to Iceberg and drop it from the expensive ClickHouse tables. So that's a really, really key innovation that allows this, that really allows us to begin using this as storage. And it also paves the way for another really important way of arranging storage, which is in the previous picture I showed you, we have a tiered storage where we have some fast storage inside ClickHouse, and then slower, less expensive, but storage for cold data. There's another way to do it, which is don't try and mix them together. Actually, when you ingest the data, write it to both places at once. Write it to Iceberg, write it to MergeTree. And so you get the MergeTree data instantly queryable. It compacts really quickly, so it's very high performance. Iceberg might get updated every 30 minutes or so. So if you have queries, data science, they don't really care about the latency of the data, they can go straight to that. And in fact, what that does is it leads us to something really important, coming back to one of the themes of the talks tonight, is how do we make room inside our databases for these new AI workloads? And the basic idea is with this double write model, you have your real-time users getting served out of the people doing dashboards where they need them to update instantly and see data within seconds of being generated. They go to the hot data, and the hybrid table engine can help with that. Your large language models, meanwhile, if they need to do inference, like through an MCP server or other mechanisms, they can go to Iceberg. Similarly, if they need to train on it, which is something, if it isn't happening now, is coming, they can go straight to the Iceberg data. And there's no load. You have a single copy of the data out there, but no load on your ClickHouse real-time workloads. So they continue to run. So that is what we're after. Here's a couple of, I'll show these again in a second. If I can be allowed 2 more minutes, I'm going to show you a couple of queries that just illustrate how this works, and then I'll put this thing back up again. All right, let me got my queries. All right, so I'm going to start. I've got a cluster set up. I have a ClickHouse server, and it knows about a swarm. Let's just start and query some stuff. Let's go ahead and connect to ClickHouse. This is running in Kubernetes out in Oregon. It's a great place. And it's going to be, we're going to start by trying to select data that is located in the East Coast of the United States on S3. This is a public data set, blockchain data, brought to us by our friends at Amazon. And I'm just going to start, and it's a bunch of Parquet files just sitting out on S3, nothing special, not using Iceberg. Just going to run a query on it. And this is a great time to thank the trade desk again, because this query will take a few seconds to complete. This is such a great venue. It's between 2 of my favorite places in London, St. Paul's and Slough House. Is it any Slow Horses fans here? Okay, I won't tell you anything other than it's outstanding. Check it out, it's on Apple TV. So this is going to take a while because we have 2 vCPUs trying to read over a fairly high latency connection. Let's give it a second to finish. Oh man, this is slow. There we go, 37 seconds. Let's call it 38. So what we want to do is speed this up a little, right? That's pretty slow. Why don't we let the swarm take over and run these queries for us? So let me go get a query that actually adds the swarm. So here it is. And I'm showing that you don't have to put these gnarly options in. I'm just putting them in so that I know what I'm doing. But here I'm enabling the swarm. You can see that at the bottom. I'm going to punch the button, and let's see how long this one takes. Now there's So it takes a little while to think about where it's going to go, because I had to read had to go list the files, which is kind of slow. But there it took 8.9 seconds. Let's run it again, and we'll start to see cache warming effects. This is going to get faster. So off we go, and so this swarm is basically multiplying the compute by 8, and now we've reduced this. We've reduced the query speed to about 7.6 seconds. Let's turn on basically turn on all the caching that's available to us, and including caching these expensive S3 list object commands. Bang, we're down to 3.8 seconds, and we should even be able to get it down to, there we go, under 2. So by adding more compute, using caches more effectively, we've just reduced this down by about a factor of 20. This is what we can do with ClickHouse with the right technology. Let me show you one other simple example, very quick, and then I'll give it up. Let's just compare running data queries against native MergeTree. Here we have native MergeTree. This is pretty quick. I'm going to write a query which is going to force me to read about 131 million rows. Just do some average and a couple of averages. It comes back in less than a second. Let's go ahead and try that in, this is now in Iceberg. So it's actually in a table that has metadata, so it looks a little bit more civilized. Let's get the query. And we're going to enable a totally cool upstream feature, which is a new Parquet native reader. It's really fast. This comes back. It's running on a 2 vCPU machine. It's coming back in about 3.4 seconds. That's way slower than MergeTree. We want to fix that. Let's add some compute. So actually, let me make sure I got the right, hopefully I had the right one. Actually, let me just double check. I think I already ran it. Nope, okay, good. There we go. Let the swarm at it. Okay, bang, down under a second. So we're now at MergeTree speed, so we've equaled ClickHouse native performance. If we run it again, caches, we'll get some cache warming effects. It's bouncing around 1 second. It's not going to go down. Let's go ahead and turn on caching fully. So this was not, we normally enable this by default in our cloud, but I've been enabling it explicitly. So file system cache, we're now down half, the response time is about half of what native MergeTree does. So this is Project Antalya. This is bringing shared object storage in the form of Iceberg tables to ClickHouse. It's all open source. We're working on it right now. So once again, here's the resources, documentation, ClickHouse repo. I'll be here till Thursday. Just kidding. It's an old American line. So yeah, I think you saw this. I won't waste too much time on the summary, but this is a really interesting time to be involved in storage because of the data growth in AI, and it requires us to build database systems that use data lakes effectively to lower the cost and allow us to be able to build systems that actually scale and don't fall down when you really need them, like on a big trading day. So that's it. Here's how you join our Slack channel. We'd love to, this is a community effort. If you want to join, if you are a C++ enabled developer, I'd like to talk to you. If you get done looking at the trade desk ads, come talk to us. We're hiring. So thank you very much, and I'll take questions.
Thank you. Thank you so much for the talk. So we've got time for 1 or 2 questions in the crowd.
And everybody who asks a question gets a T-shirt.
Definitely ask a question then.
All right. Who gets the first?
Can you elaborate on C++?
Here's your T-shirt. Yeah, so why do we need C++? ClickHouse is written in C++. So what we're looking for is a database internals. Folks, we're hiring across the board, but I think a really key thing for building a system like this is you have to change ClickHouse itself. We also do a lot of stuff around it, like we write Java, we work in Kubernetes. There's a lot of stuff about building systems that actually run, but in the end, you have to alter the core of the database. So that's why we have kind of a sick interest in C++ development. You have to ask the question now.
Hey, so my question is, Is there any merging process of smaller Parquet files after the ingest, similar to merging in the merge tree?
That's a really wonderful question. And actually, one of the reasons why we chose this model to support first, where we read it into MergeTree and then basically replicate it out to Iceberg, is MergeTree compacts it for us. So we are going to add merging into Iceberg itself.
Okay, or you can fall back on S3 tables as well. They do.
Exactly,
Right.
exactly.
My second part of the question I wanted to ask, when you query along primary indexes, do you skip row groups, similar way how you skip granules when you query?
That's a wonderful question. And it turns out that in Parquet, so you've obviously done this before, Parquet does not have a sparse primary key index the way ClickHouse does. So the answer is we just scan the row groups and we basically knock them out using min-max.
Okay.
So it's less efficient than using the sparse index, and we don't have a way to find, basically to locate segments quickly. I think we'll put that in eventually.
Nice that you shut that question.
I've got more.
I do have a real question, but first of all, just a side point there. Have you looked at Pallet Jack for exactly that problem? Because we have exactly that problem, and Pallet Jack basically gives you a thing alongside Parquet files which lets you do skipping. So you might just be able to use Pallet Jack.
Oh, yes, I have not. And in fact, can I talk to you about that afterwards?
You can.
Yes.
But the actual question I had was, how does this compare to the shared merge tree that they're making at the premium ClickHouse?
Yeah, it's the same idea. And so the difference is there's two big differences. One is what we're doing is going fully into open source. So you don't have to go to somebody's cloud to run it. But the other thing, and I think this is a kind of key design difference, was we actually started out to try and rewrite shared merge tree in open source. It turned out hard, but the more we thought about it, we thought, hey, that really isn't the right way to go, to have another proprietary format that basically is where you have to have ClickHouse as a gatekeeper to give you access to it. It just makes more sense right now to use an open table format because of the fact that you've got all these workloads that need to see the same data. And I have people literally telling me, look, give us a single copy of data, SQL interface, that's what we want, and let us have access to that data regardless of the workloads. So I think what's happened is the market has evolved a bit since they made that decision. And so I think if they made that decision now, they might take the same approach. In fact, maybe they will. I don't know. They could actually open it up and make it look like Iceberg. So that's basically the answer.
Nice. Thank you again.
All right. Thank you.
So we're going to have a small 5 to 10 minute break. Feel free to grab some drinks and whatever food is remaining.
1, 2, 3. No.
Right, a bit too.
Does it actually? I don't think
It does.
Ah.
I think it's even closer actually, which is weird. 1, 2, 1.
Oh well, it
So I
tracks
think
you
it's
better.
Steven.
1, 2, 3. Okay.
Quite close.
Oh, that would be.
Oh, did don't know how Robert did it.
Did he maybe? 1, 2, 3. No, this doesn't really. I think.
Handheld mic.
Oh, that would be.
If I can find him.
Yeah. That's all,
Okay,
like
let's
if
try
we
making
cannot do it, then of course I can
Before
try
pinching,
this.
do you want to try speaking right here?
1, 2, 3. No. 1, 2, 3. 1, 2. Like it's like
Yeah, should be it's too close. One, two, 1, 2. Yeah, this works.
yeah. Okay.
Okay. Let you switch it on. Hello, hello. I hope you're all enjoying the evening. We're about to start the second talk. If you could come find your seats. Nice. So for our next speaker, we have Olena, who is a staff developer advocate at Confluent. So she's a recognized expert in data streaming and analytics. She has over 2 decades of experience in software engineering, and she is very good at teaching people about tech. So if you want to come speak to her, please do. Talking about teaching, her talk is going to be about teaching databases to speak human with LLMs and MCP. So how do LLMs hold a conversation? And yeah, basically that's it. How do LLMs hold a conversation? Let's give her a warm welcome.
I forgot to press the button. Okay, now it works. Hello, everyone. Yes, my name is Olena. I work at Confluent, and we actually do a lot of like very serious stuff with data streaming, data storage, data processing. However, today I wanted to touch a topic somewhat lighter. I also added some pictures of cats because it's late, and I hope to keep you awake. But we are going to talk about a topic which is actually evolving, and I see it being implemented more and more. However, it's still kind of the first steps, and we're going to see more of the usages of LLM for LLMs of analytics, but kind of understanding what stands behind it, and just also seeing kind of what you think about it. So starting with a use case. And here, I would say it will not be about the needs of engineers or at least not those who cannot do analytics on their own, but rather we are going to talk about some kind of like needs or maybe of a management, or people like in higher positions who actually want on the fly to be able to ask information about the data. And for example, a CTO during a very important meeting with shareholders would like to know what is the month by month fee income from a certain date to certain date for some period of the organization and with some conditions. So it's kind of a phrase in English. And then what if we would be able to translate that to SQL and make a request to the data storage, data lake, or whatever, a place where we are getting that analytical data and get the response. And we can actually do it. We can use LLMs, and we are going to look at the scenario where we are having a streaming real-time data from some kind of a financial institution. In this very imaginary scenario, it's a cat-run financial execution institution, and it's here we get the data which goes into some kind of a streaming system. And from there onward, we store it for data analytics, and then we can connect our large language model to that storage, be able to send those requests and bring the response to the person who asked that through a large language model, through a chatbot. And here, large language model will play an important role of being able to figure out the schema of the data, to be able to translate the request and do multiple other things. However, the whole flow is also quite important, and here we have some important components such as MCP, as well as I'm going to use Apache Kafka to bring the data. I am going to rely also on the Iceberg, and for the MCP, I'm going to use the query engine Trino. I should probably change this and use ClickHouse, because ClickHouse is amazing, but it's like my old demo is written with Trino. So looking at this demo, and this is kind of looking at the scenario, this is the use case I want to talk about. And the demo looks like this. So we are going to ask, I already have a data stored. We will look a bit deeper step by step later. But generally, like I'm asking here, Claude from Anthropic, what is some value for Bitcoin price today? I, to be honest, don't know much about cryptography or like crypto currencies, but this is like I have a ton of data from APIs. And Claude can actually figure out the like to understand the request I sent to him and also find what kind of data it has access to. It makes some errors, so actually it fails to retrieve, but it doesn't really give up. It tries again with the different approaches, and eventually it gets understands the data which we have. I also have a couple of tables in the data set there. So it figures out which one, which table is better to use, on which frequency the data is being populated into the table, and writes the queries to retrieve that information from the Iceberg storage using Trino. So this is kind of an idea. So we ask the question, then LLM actually goes and tries to figure out that the answer based on the data which exists there. And if it finds the data which kind of fits for that question, it returns that information. I played with numerous different setups. So generally, like, of course, it depends how well LLM is like knowledgeable about the domain and other things, but we are going to talk about those limitations a bit later. So the first kind of challenge to make this work, and this is already of, even though it might look futuristic to some of you, It's actually the applications which already exist. And I was recently talking to a person who is working for a bank, and they actually right now also creating a setup like this. However, there are quite a lot of challenges still to solve, and it doesn't really work like perfectly. So here we are looking more or less at the stage where we are evolving, and we are at the stage where it's usable, but with a bunch of challenges. So the first one is actually translating correctly natural language to SQL. And here, for example, like if you have a very simple phrase, show me all customers from Germany, an LLM is quite capable to translate that and map correctly those values. So LLMs are trained to recognize the patterns, so they're really good at doing this stuff, at least at the simple level. The more complex we go, the more challenges we have. And we have, for example, ambiguity in the language. So when you are writing that request, you might use different table names and what you have in the storage. For example, that CTO cat from the initial slides might not really exactly use precise words to describe what we have in the schema. So LLM should be smart enough, or we should give it some hints on how to analyze a schema. So then, apart from the schema, which is kind of a challenge, also we have the complex and nested queries. So the more complex the query will be, the more potential for LLM to write it incorrectly. And also, LLMs are amazing at hallucinating. So at saying something very confidently and very wrong. So this is kind of a challenge. As we will also see right now how well we are doing this, but still. So then joins, any complexity there. Also writing the queries which are performant rather than kind of slow. The more complex stuff goes, the more difficult it is. So a bunch of challenges. However, when we look at the timeline, how actually we are doing with translating text to SQL, we actually, so like quite a long time ago, like 20 years ago, they were still like using rule-based, where you programmatically try to predict all possible scenarios, like, and kind of translate what a person types or like whatever, like text into a SQL, trying to go with maybe a lot of if else and kind of like this kind of graph structure where you manually analyze the data using synonyms and so on. However, that was very inflexible. And right now we are in this LLM era where we made a huge progress. And ever since around 2018, we are seeing more and more models which actually are capable of translating text into SQL. We can evaluate it looking at the benchmarks. So back in 2017, there was a benchmark for WikiSQL, and that benchmark was not really complex. It's like it was actually like looking into that 8 years later. It was like tasks for nowadays LLMs, but at that point of time, it was complex to solve. And then we got Spider, then we got CoSQL, and now BERT. Every benchmark actually is more and more complex. It has more and more complex text translations and kind of data sets which models should solve. And seeing how models are solving that, we can see how we are evolving. So here on the y-axis, we have this percentage of correctly solved problems. So WikiSQL data set, and when the sequence to SQL model was attempting to solve it back in 2017, it actually did like 60% correct translations from text to SQL. Then when the same model was attempting Spider, which already included like more complex data sets and more complex stuff, it kind of like the prediction went into like around 20%. So it was like, if you don't really want a model to have only 20% correct responses for your questions. So, but in general, like with every year, For example, with Spider, for example, T5 large was able to solve like around 75%. Then GPT came and it really was good, like over 80% of correct responses. But then the same GPT, when attempted on BERT, did way worse because BERT became more complex. So every benchmark has more complexity. And this is kind of where we are moving into more like real world scenarios, or at least BERT is kind of focuses on this real world use cases where you actually also care not about like just translating SQL, text to SQL, but translating in a way that the SQL is quite performant and kind of can run fast on whatever you have. So, and also, yeah, like there is way other more metrics how we evaluate it. So BERT SQL, for like those of you curious to look into this, pretty nice benchmarks. They have also a paper about it and some code repository associated, so you can run your own use cases. And they actually assume that human performance will be like around 92%. It will really depend who is that human who is writing that SQL. So I don't think that I will do 92% of those. But I guess they have a good selection of those people. But at the moment when I took the screenshot, which was like maybe like a month ago, that's still the best model did around 77% of the test part of data set correctly. So, and we are going up and up. So this is like with every LLM, we are doing better. So there is a huge promise there. And so that part is kind of works. Now, to connect our LLM to our data storage, we can do it in numerous different ways, but MCP probably is the most convenient way right now to introduce tools to LLMs with kind of a bit more like established protocol. How many of you actually used MCP so far? Okay, we have some hands. Good. So MCP, for those of you who are not aware, this is where we actually expose a set of tools, kind of APIs for our LLMs. And those set of tools can be like anything. It can be like Google Maps, or it can be something quite simple like some kind of fancy calculator which does something weird with numbers. So whatever you have, you can expose as APIs there. So ClickHouse has MCP, I checked, so that's again, my plan is to rebuild this demo a bit using ClickHouse later. So an MCP generally has, like, there is a host where we set up a clients. For example, Claude can be a host, and then I set up a client as a server for accessing. It can be like a client for ClickHouse MCP, and a server, then we connect to the server for ClickHouse MCP. And you can have as many of those as you need. So this is the way how we can access different types of like different like it gives us extra context. So in general, like what MCP does, it provides us tools to retrieve extra context for the model, and then model can make this either based on like whatever you have in your file system or data storage or whatever extra tools you are using. So here I'm relying on Trino MCP because Trino I used as a query to query the Iceberg storage. There are different MCPs available. Something which we should be very careful is not really like blindly trust an MCP, because generally like you will take some binary file and then you will install it on your computer, and that's a lot of recipes for disaster. However, if you trust the MCP, you can set it up either locally or you can also use it remotely. And this is, for example, how the MCP setup looks for Trino for the use case which I use. So like you have just JSON object, and then Claude knows that it has access to those MCP servers, and they have like a host, post, portent, and schema, and so on. So, and this is what kind of then Claude uses to access the Trino. Here I used Claude LLM. However, a lot of LLMs right now support MCP, and you can use those. So now talking about the data which comes here. So, and in the demo which I used, I actually was getting cryptocurrency data, and I used like I sent them to Apache Kafka. How many of you have used Apache Kafka? Or okay, have plenty of hands. So Apache Kafka is a system to move the data across numerous multi-services. Like, so kind of whatever you have, you can move the data across your systems, used in the industry quite widely. And if we have to kind of explain how it works, you have producers which produce the data. For example, whenever you are paying with a credit card somewhere, that can initiate the data, and the data package goes into Apache Kafka topic. And on the other hand, we can read the data and do whatever, like for example, anomaly detection with that. And the topic itself is split into partitions so that we can process data, or like kind of move data as fast as possible. So we don't have only one lane for the data, it's kind of multiple lanes. And also by changing the number of producers who bring the data in, and by changing the number of consumers who take the data from Apache Kafka, you can kind of make this more lanes for your data to go through or less. And in this way, it's like a pipe where you make the pipe bigger when you have more data during, for example, peak hours for your system, or when you actually make the pipe less, when like during the night, for example, if your shop doesn't have any activities and you don't want to waste resources. So Apache Kafka is designed to be very, very fast and efficient for data streaming. So, and I played here with an example of using a CoinGecko API. I created a connector, HTTP source data just to read the data, and got that data from the CoinGecko as an example, so that I have a bunch of data which is possible to analyze later on. And so with that, the data was flowing. I had kind of this from the particular API, a JSON with different coins together. And what I did, I also split it into a smaller, using Apache Flink, into smaller JSONs just per single coin. So I had those two tables, which actually then MCP could see and figure out which one is better to use for the particular questions which I asked. Now that data through Apache Kafka goes into Apache Iceberg storage. Apache Iceberg, I feel, doesn't need to be introduced here. We already talked, Robert gave a really good introduction to that. So it's a really great technology to unify data warehouse and data lake. I love Apache Iceberg and the concept of it. So with Confluent, we actually connect Apache Kafka and the Apache Iceberg storage with Tableflow. So behind the scenes, we just send the data from Apache Kafka to Apache Iceberg to the storage and S3, and then or like whatever storage you select. And then you can make those analytical queries there. So this is how the data gets into Tableflow. And then we can use any query engine which we want with Iceberg. Plenty of those are available. they have pros and cons and different preferences for people. I used Trino here. And this is how actually with the Trino, I was able to query the storage and also data with cryptocurrency and get that information through LLM. So this is kind of the whole idea. It's quite simple. However, there are some challenges, and now I wanted just to talk about those challenges. So when you if you start creating this system for yourself, you need really to think how you're going to evaluate that LLM is going to retrieve you the correct information. And because LLM hallucinates a lot, we need really to make sure that, first of all, when we are selecting the LLM or when we are changing, or maybe you are fine-tuning LLM, you have some kind of a benchmark, your own benchmark, to compare that it retrieves you correct information, or at least according to that benchmark, you have a good percentage of right answers. So that would include some kind of a domain-specific suite where you can have metrics for the accuracy, like if it kind of includes all the columns, if there is any syntax error, then also if it really gets the correct data from the storage, and in general, it might be writing the right SQL, but not really giving a useful direction to solve the problem. And then also we have issues with wrong join keys, time granularity errors. So all those things you can actually test using your specific part of your data set and kind of to see if it goes the right direction. So that would be the way how you can validate if it's actually doing what you want it to do. Then with all that, we need also to take care about security and governance. And this is actually where just MCP is also accesses your API endpoints. And when you rely on something third party, especially if it's not really your own written MCP, but something else, it can include a lot of malicious stuff. And not only that, actually, the LLM itself, if you, for example, rely on the open source LLM, you need to know the origins, how it was trained, and in general that you can trust it, because actually it can be also injected with something which will hijack that LLM and try to do something bad with your data. Either expose your data and bring it out to some other source, or I don't know, delete some sensitive information. So make sure that you trust MCP, make sure you trust LLM. But also when we use MCP, for example, we can set different permissions for different roles for people to access the data from your data storage. So we need to give as little permissions as always, like for all other APIs. So you consider MCP just to be another API, and you try to restrict access to the data as much as possible to allow only that access which is needed for that particular role. Also for the sensitive information, like sensitive data names and so on, you don't want to expose it unless it's really needed. And I guess in majority of the cases, you don't really need that. So there is a lot of security issues which can happen. So that's why this is one of the probably major concerns. But with usage of LLMs in general, we right now have a lot of issues which arise with security. So yeah, so if you decide to adopt, start with one small curated data set, something simple, so that you can keep the whole surface area small. You can use that benchmark to evaluate if it really works, especially if you are again, trying different LLMs, or you are in possibility, it's not for everyone, train your own LLM or fine tune it on the specific domain which you have, then you can use that. Keep the security only read-only user. Try to keep the response like smaller. It doesn't have to be 100, probably it should be bigger than that, but you can keep so that LLM doesn't really retrieve you a huge amount of data unless you really like verify it and trust it. It doesn't retrieve you like the whole data set. And I mean, we know that ClickHouse deals quite well with those laws, but still, you don't want to overload as a system. So yeah, just be vigilant on what exactly you expose and what exactly is being used. Also, for example, with Claude, what is nice that actually they show which SQL query LLM created, so you can look at that query and actually you can see if it makes sense. But again, as a person like who understands that SQL query, but that analysis is nice to have, and also like to have a trail of what was run so that you can evaluate this for later. So that's the idea which I wanted to share. I see it implemented, like so see it being implemented and also implemented in some places. We will see, I guess, more of this technique of using LLMs to like be kind of a business intelligent UI to get the information from your data sources and analyze it, especially for those people who are not really good with SQL, or for those who really want like faster responses. So I hope that you found this interesting. I do have a couple of links in case you want to try Confluent and try Kafka, Iceberg, Flink. This QR code will give you some extra credits to try it out. We also have a very nice, I know I probably like, maybe if you decide not to join neither Altinity, so we also have some office in London, and in case you are interested in data streaming, ask me about it later. That's it for me. Thank you.
Nice. Thank you very much for your talk. We have time for 1 or 2 questions. Is anybody in the crowd? Oh, go for it, Robert.
Yeah, I have a question about LLM upgrades. I don't, have you run into this where, you know, like what happened when GPT-5, ChatGPT-5 came out? OpenAI said, oh, we're deprecating everything before that. And this caused panic among some of the people that I know who are involved in this, because they can't really control when these upgrades happen. And then all of a sudden, this non-deterministic model shifts to another non-deterministic model. So do you have any experience with that and any advice for people about how to deal with it other than panicking?
Other than panicking, more panicking. So I think actually this is where I think that benchmarking the solution which you are, whether it is we are talking about analytics or any other thing which you are using LLM for, if you have some kind of a benchmark where you run, so you evaluate how LLM is working for your particular use case. And then you see where it works well and where it fails. So we have these tools for evaluating LLMs, plenty of those. And it makes sense because I don't think that there is a case that you can still use the deprecated model when they remove it, access to it completely. So you will have to move to another model. But then at least you will have a comparison. Is the new model does as good as the old one, or maybe it actually does even better, or it actually goes completely like bonkers, and then you have to find some other solution. So, but like I don't think that you can really like find a way to stop unless you want to use like open source models, but they have other issues. And also sometimes the updates in the models are needed because there can be like security issues again. So this is like with any other product. So I don't think we should fight with the fact that they are going to deprecate it. It's more that we need to be able to compare when we start adopting a new LLM, then it is working at least good comparing to the old one. And for this one, having those like evaluation system, your own like benchmark with your particular data is where it will help.
Nice, thank you. Any other questions? I've actually got one for you. in case. So we're all engineers. We love the idea of using LLMs, MCPs, anything AI related, but often it kind of stays at the POC phase and doesn't actually evolve into production uses. Where do you think is the industry or the area where the use of LLMs and MCPs is most likely to be widespread, adopted, and get pushed out to production in the LSM?
I have a feeling when I was looking at the list of MCP, and MCP it's not exactly the newest technology, but it's like around 1 year old, I think. So it's still fresh. And I think that the list right now, when I was looking, it's like huge. That's why it's actually, I think that MCP and generally using tools will be adopted like anywhere we need access to the external data. So it's actually like a huge variety of the solutions. Even for example, like when we use LLM and LLM needs to access to the some websites or like the intranet. This is technically also a tool which gets you information from external source. So it's like from the basic stuff to more specific ones. For example, getting that information from ClickHouse, from Iceberg, from Kafka. I also see people do it, and I'm still not sure what I am thinking about it, like setting up the infrastructure. Like I'm more like a Terraform person rather than using, but there are some actually where you can talk to LLM and it will tell you all the information about your infrastructure and help you change the resources. So there are a lot of, I think, experiments which kind of look fun, but there are also a lot of things where we just need that external access, and that's where MCP and LLM will work quite well together. But yeah, we also have like other tools like agent to agent, or right now I think Claude introduced skills, which is kind of also interesting direction. However, I think still that MCP is the most powerful out of all of those because it just opens the door to use whatever you need in combination with your LLM.
Great, thank you. And let's give another big thank you to Olena.
Thank you so much.
So we'll just have one last 5-minute break before we have our last speaker of the evening. So feel free to grab some refreshments. Apache Iceberg. Iceberg is very popular this evening with Amazon S3 tables. So let's give her a very warm welcome.
Thank you. Okay, so let's get started today. And we have been talking about S3 tables. We have been talking about Apache Iceberg. What I'm going to do here today is I'm going to walk you over through the managed solution provided by AWS for Apache Iceberg, which we call it as S3 tables. ClickHouse, Altinity does use that solution in order to store their data sets, which is in the Parquet format. So when we build Amazon S3, and just give me a show of hands who's using Amazon S3 here. Okay, I like that. But yeah, since we built Amazon S3 in 2006, the primary use case for Amazon S3 was storing a lot of unstructured data, I would call it as, whether it's ranging from medical images to video files to static content or any part of it. And that's exactly the use case which we thought Amazon S3 would be used for. But as we started talking to our customers, and in 2 decades of time, what we really saw, and you as our customers actually amazed in it, a lot of customers was using Amazon S3 to store the data in a tabular format in Parquet. That means in an Iceberg format or in tabular format, which we talked about. I think Robert briefly touched about columnar data and row-based data. So a lot of data set was stored in a tabular format. When we did a lot of discussions with customer, we found about exabytes of data is ranging from exabytes of Parquet files are actually stored in Amazon S3 in there. And that really led to the innovation or the thought about, okay, why don't we give our customers something what they are building on? And that's the thought process of Amazon S3 tables came into place. Right. Robert has taken all my questions. As you can see, I did have those questions. Who has heard about Apache Iceberg? Who has heard about S3 tables? So I need to reinvent those questions again. So I'll go back and ask you a question here. I know in the room, a lot of people now have heard about Apache Iceberg, have heard about S3 tables. But who has heard here about Hadoop, HDFS? Okay. I'm able to guess the age as well of the room now. So it all started with Hadoop and HDFS. So if you go back in 2008, I guess that was where Apache Hadoop was in picture. Or if we see Spark, that was 2014. All of them worked on a model or a concept of HDFS as their primary data store rather than as Parquet data store, right? But it did bring in the complexity with it. So what do I mean by the complexity in it? When you have any HDFS data store, you would have to extract the data, load the data, whether it's an ETL job, and then put it and process the data set, and then put it into your data store to do it, right? This led to the logic, complete logic being complex. Plus, along with that, the cost of the solution increased. And it was a little inflexible in terms of the data being bounded to just one particular storage type, giving less flexibility and innovation technique. And that's where really Apache Iceberg really shines, because as you can see on the screen, they're all question marks, but these are all the capabilities and features what Apache Iceberg bring into. Robert did a very good dive on Iceberg, what it really brings in. There are a few key pointers which I would really like to highlight here. First is atomicity. Iceberg in general is very atomic. So any change which you're making into Iceberg would result into a commit, and a commit would basically result into a snapshot. I'll be touch basing about, okay, how the life cycle of a snapshot on Apache Iceberg looks like just in the next slide. Second, I would really like to talk about its engine agnostic. What do I mean by that? You can have multiple Iceberg-based engines interacting with it. Any data which you have in the open table format, you can interact with it, so whether it's Parquet data and engines like Spark, Trino, Flink, Kafka, Athena, the first parties of AWS, or the third parties, whether it's Snowflake, DuckDB, ClickHouse, all can be integrated with it, right? It's an open source, so it's a community which is continuously maintaining and updating it. So it's open source, it's easy to use. It's an open API, so you can integrate with your own applications the way you want it, rather than being bound to one particular application set in there. Scalable and maintenance, I think that's one bit which has not been talked about here, and I'll be doing a little bit deep dive about scalability and maintenance in S3 tables as well. Scalability is an Iceberg in general would scale in a way where you can have compression and you can have the data being managed on its own. So let's see how all of that is done. Giving an overview about a table. So we had a brief moment where we talked about catalogs. We had a brief moment where we talked about metadata and the data partitioning. Apache Iceberg uses a transactional log model. So what do I mean by that is, anything what you are changing in an data set would result into a commit, and then it would result into a snapshot. So if you see, a snapshot would basically include a metadata.json. The metadata JSON is basically the table metadata here. While the manifest list, if you see, it's kind of a list of manifest file. Any changes which is happening on your manifest data would be a part of the manifest list. The manifest list would point to the manifest file, which in turn would point to the data files. There are few features which Iceberg does provide, which are known as snapshot generation or orphan file removal, which will help you in the storage management of it. So let's say if you're using a general purpose bucket and you have Iceberg on top of it, and if you want to manage it on your own, these are the features which can help you to have your storage cost in place as well. So you can use these features for Iceberg. The other feature about Iceberg, and this is very heavily used in S3 tables as well, because that's exactly the way you'll integrate with S3 tables or interact with S3 tables as well. The modes, how you update, write, or copy into S3 tables, right? Because that's a big part of it, how you're interacting with it. So when I talk about an update, read, or write, there are two methods. One is a copy on write, and the second is merge on read. What's the difference between the two? The first one, that is the copy on write, is kind of a default mechanism for Iceberg. It's used on its own. So as the name suggests, any data which is changed, the complete table version would be changed. And I'll show you that with an example as well. While with a merge on read, what would happen? Just a particular data set would be changed rather than the complete data on it. So let's see how it really looks like. So let's say you had a table version 1, and you had a data set which goes as Prachi likes apples, Sarah likes oranges, John likes berries, right? And you were in a crazy mood and you wanted to update Prachi's favorite fruit as banana, right? When you do a copy on write, so that's the default mechanism in Iceberg, what it will do is it will create a complete version. It will delete everything what you had in version 1, and it will create a new version, that is version 2. So it's kind of, if you see, write intensive, and the performance can be a bit slower because it's basically rewriting all the data what you had in the table version 1, right? While on a merge on read, what would really happen here is, and I'm using the same example where you had the table version as Prachi likes apples, Sarah likes oranges, and John likes berries. If you do an update where Prachi likes banana, in this particular example, the data 1 would basically remain the same. However, there would be an insertion of the second data which is just being updated, that is Prachi likes banana, and there would be a delete marker being placed, which basically is kind of invalidated by the delete file. So anything which is changed would be captured as a delete file, and there would be a position placed in the table in itself, showing that you're just updating one particular row or one particular column depending on the data you're in. So this would be a little faster. It also has a flexibility of being better in terms of cost and in performance as well. By this mean, it does not mean you can't have multiple tables using both. So in a table bucket, you can have both the methods going in parallel depending on the workload you have. So let's say if you have a write intensive workload, for example, then you can actually choose between the two modes which you want. And if you have a data set which is updated very quickly, you can actually you can go for a merge on read update where it just changes particular bits rather than changing the complete table versions as we saw for copy on read as well. Okay, so let's move to S3 tables. What is S3 tables, right? S3 tables is a fully managed Apache Iceberg offering provided by AWS. It's a new bucket type, so do not confuse it with a general purpose bucket. It's a new bucket type, which we call it as table bucket. It is the first class citizen of AWS. So what do I mean by that is it has its own dedicated ARN. You can use its endpoint in your own applications through APIs to interact with it. You can use the same access policies like you use in a general purpose bucket. So it has a table bucket policy which can be applied. You can also you can also interact with it or have security-based use on IAM policies as well. And along with that, it also has a dedicated endpoint. Like I mentioned, it's regional. So s3table.region.amazonaws.com is the endpoint, which you can use in your applications as well. Right. So I've mentioned this a couple of times. It's a fully managed Iceberg offering. There are key few pointers which I would really like to highlight here is the performance part of it. So S3 tables provide 10x transaction per second in compared to general purpose bucket. What do I mean by that is, if you see a general purpose bucket, and I could see a lot of people here are using S3 general purpose bucket, so they might have run into problems like 503s or transactions, TPS. S3 general purpose bucket has a read of 5,500 reads and a 3,500 writes per second, right? However, with S3 tables, you get 10x times of that. That means you get 55,000 reads per second and 35,000 writes per second out of the box. And that does not stop there. It scales further like a general purpose bucket as well. Second, APIs to manage. So there are dedicated S3 table APIs as well, which you can use to manage the tables. So whether it's create table, whether it's putting the maintenance or anything of that sort, you can do it using your applications as well. Manage compaction. So when we were talking Iceberg, I said, okay, there's a feature as maintenance, which Iceberg does provide, and you can use that feature in order to maintain as well. However, that is something which you would have to manage if you're using a general purpose bucket on Iceberg. With S3 tables, it does have a feature of own managed compaction, and you can choose the compaction type which you want. So there are 3 compaction type as of now which are available, ranging from bin, pack, sort, and z-order, and I'll talk about these 3 going further. Governance and fine-grained access control. So S3 table is integrated with Lake Formation, Amazon Lake Formation, and SageMaker Unified Studio as well, giving you a better integrated fine-grained control. So using Lake Formation, you can have table level and bucket level granularity as well, and column level granularity as well. So you can go ahead and if you want certain users just to have access to certain tables, you can actually make use of Lake Formation along with S3 tables and have those particular settings in place as well. IRC endpoints, that is the Iceberg REST catalog endpoint. I know Robert talked about catalogs and how they make use of their own custom catalogs in order to integrate with with ClickHouse and along with S3 tables. This is the endpoint which actually would help them to integrate that particular connection between ClickHouse, S3 tables, and Altinity in there, right? Third-party integration. So if you have a customer who uses, let's say, ClickHouse, or who uses Snowflake, or uses any third party, that is all integrated with S3 tables. So that you can just have S3 tables as a data store and then make use of any third party to integrate with it. We talked about MCP servers just way back. So S3 tables does support MCP servers as well, and you can have like normal language queries and fetch the data from S3 tables from there as well. Okay, so we announced S3 tables in reInvent 2024, and if you see the momentum for S3 tables, it has been pretty huge. This slide might be a bit outdated. I think I need to work on it a bit better and update it. But I would really like to highlight few key features here. First being the integration with SageMaker Lakehouse. That was in March 2025. We do have customers who are literally using the complete warehouse kind of solution with SageMaker Unified Studio. KMS support, IRC endpoints, and the latest being the support for MCP servers, compaction for Avro ORC, and the support for cloud formation and CDK as well. Okay, so there would be few features which I'll be talking about S3 tables, which can help you in your storage cost and performance. When it comes to storage part of it, the data being stored is the primary cost which would come up. So like a general purpose bucket, S3 table has 2 costs, 3 costs actually, but I'll talk about the first 2, which you see in S3 general purpose bucket. First being storage, second being API. Those are very similar to what you have in a general purpose bucket as well. The third cost comes from compaction, and that's kind of a management cost as well. I think that was in the month of March, I guess, if I'm remembering the month right. We have reduced the cost as well for compaction to 90%, which means that it's kind of very negligible for the compaction bit as well in there. So that includes the management cost as well. So that would be the 3 costs. Now, on top of that, you can also manage your storage cost and optimize your storage in 2 different ways. First is Amazon S3 table does a periodic maintenance, whether it's removal of your snapshots or a removal of your unreferenced file removal, right? So I think I've been saying this as a broken record, Iceberg equal to atomic transaction equal to asset compliance, which means every commit would result into a snapshot. The more number of snapshots you have, there could be the more storage you're using, the higher the cost would. So the first feature which you have, that's a snapshot management. It's really important that you manage the snapshots in the way you want. So it has 2 parameters in it. First being the minimum snapshots you want, and second being the maximum snapshot age which you can keep. Both the parameters, when they are satisfied, the snapshots would expire automatically. You don't really have to do anything. S3 tables would manage it for you. Similarly goes the case for unreferenced file removal. Any file which is unreferenced, Amazon S3, based on the parameters or the configuration you have, would take care for you and would remove it. These parameters are enabled by default. However, they are configurable. You can go ahead and disable it if you want, or you can change the values to what you want. I would really like to call the table maintenance configuration as required. Every customer who's using Iceberg or SC table should be using this feature because it does really help you in your storage optimization and cost as well. Right. The second feature which I would really like to highlight is compaction, because compaction does help you in performance. So the way S3 table compaction works is it looks for small files. The number of small files you have, it will merge into one bigger file, right? By default, it works on the target file size you have, and that's default is 512 MB. However, there's a range which you can set in your configuration. Again, this parameter is configurable. You can change the values, you can disable it. If you want to bring your own compaction, you can do that as well. That's also allowed. It's a continuous process, so you can't, it will run periodically and then see the number of small files which you have and then combine them. It runs every partition rather than on a complete bucket. So think of in a bucket, you have multiple tables, and inside a table, you would have multiple partitions where the data would be written. So the compaction would run on multiple partitions rather than on the complete bucket which you have. Right? What's the impact of compaction, right? So a lot of, when I talk to customers, they're like, okay, why do we need compaction? The main reason is, first, it helps you reduce the cost as well because it's clubbing small files into one big file. Second, the number of requests reaching S3 would be less. So I think Robert mentioned a very good point about list objects. Whenever you're trying to retrieve anything from S3, list operation is a costly operation, and it can be a slow operation as well. With this particular feature, the number of requests which reaches S3, the number of times you have to do a list is less, thus helping you retrieve it faster, and the latency and the throughput also is better in that particular case. Okay. So if anyone remembered the slide where I had S3 tables, 3 type of compaction, first being bin pack, second being sort, and third being Z order, and that's the time, here's the time I'm going to talk about all 3. Coming to bin pack, it's an efficient compaction. It's default. If you do not change any parameter configuration, this is what S3 tables would be using. Now, the primary goal of bin pack is to really address the small file issue. How many of you work in a media segment or work or have seen the small file, like having a lot of streaming files coming in and you see, okay, they are getting accumulated? Have you come across that particular kind of issue? Okay. That is, at least I got one hand, thank you. So, but yeah, so that kind of thing is something what bin pack would really solve, because any number of small file, and that does not relate to media, it could be transactional data, it could be investment banking data, any small number of files which are being ingested, it would basically club together and put it into one. That's the primary goal of it. It does not reorder anything. As the data comes in, the data would be merged into one and kept into one. So think of it in terms of the use case. I would say any general workload where you do not really need to worry about how the data needs to be categorized or ordered, perfect use case for it. In terms of performance, it does help you in performance as well, because the files are getting merged, and you, like I said, you don't really have to go back and check all the small files which are there. Rather than, it will just pick up that one big file to read the data. Coming to the second one, that's sort, right? As the name suggests, it's rewriting the file based on the sort value which you give. If I really want to give an example of a sort, okay, we can see it here on the screen as well. And I hope people on the Zoom are also able to see it. But think of it in terms of you have 3 different columns, like a ID, date, and region. And the data is coming in a very unstructured or just in a random way. However, you can choose a particular key as a sort key. Here I have chosen the date as the sort key. So anytime the compaction would run, it would basically see the date key as my primary column key and would merge it on that particular key in itself. One thing which sort does here is it enables skipping of the data set, helping you with further improved performance. So if you have a workload where you're like, no, I just need the performance to be the optimal, that's where the sort is actually a good use case, because it does allow you to data skip, helping you in better performance in there. Okay, Z order, at its core, think of it as a Z. You don't know which keys you want, but you want multi-dimensional kind of sorting in place. So think of latitudes and longitude. If you want to have a compaction based on two different undimensional keys, which match, which do not match, Z order is there. I think Z order is a bit costlier as well. I am forgetting about that, but I can double check. But the primary goal is to basically optimize for multi-dimensional use cases in here. And that's the core part of it. So it's kind of a Z order columns to perform better than a random layout, which you would have in a bin pack, for example, in there. The use case for Z order is more on analytical workloads, where you have multiple columns, where you want to combine them. Like I said, latitude, longitude, if you have that kind of columnar data set, Z order is a good use case. Z order compaction is a good use case to do that. Okay, so we do take care of everything what you would have to do. So if you would have to run the management, Amazon S3 tables would run it for you. Compaction, yes, we would do. But that does not stop you from configuring it at your end as well. So if you want to change any parameters, you can make use of AWS CLI, you can make use of Boto or any API part of it in order to maintain it. On the screen, there are two examples. First is how you can check the maintenance of the table, if the maintenance has run on the table bucket or not. So the API which you see, that is get table maintenance status, would help you understand if the maintenance has run or not. However, if you want to select or if you want to put any maintenance configuration, the API which you would refer to is the second one, that is the put table maintenance configuration. And in the strategy part of it, you can specify, do you need a bin pack, do you need a sort, or do you need a Z order, depending on your workload again. So that is where exactly you would have to set it in terms of them. Right. So I talked about how you can do the performance a bit better. However, there are few other knobs which you can turn in order to have better performance. And I'm not going a little bit deep into this, but the most common things which you can adjust is the target file size, duration mode, column stat limits, the compression code as well. And those parameters which I've just listed out do have the biggest influence on performance and manageability. So always tune your data set based on your query patterns, your data size, and what you're trying to expect in terms of the performance return investment as well. Okay. This is one of the common use case which I see with customers a lot when I talk to customers. I do talk to customers from all the global spheres as well, but this is the use case which comes up the most when I'm talking about S3 tables. And that's a streaming analytical workload on data lake. Here on this particular diagram, what you see here is it's an architecture which talks about a data producer basically inputting the data to an MSK, which is being generated and using EMR as a structured Spark sequence to put the data into S3 tables as the data store. Your data producers can be anything. It could be a Kinesis Firehose as well. It could be your EMR. It could be any part of it, which is again putting the data into your Amazon S3. Earlier, before 2024 S3 tables was launched, customers used to use S3 table and then used to run ETL jobs to process the data and then put it into a new S3 bucket, change the data type, which used to add a bit of complexity, cost as well. With S3 tables, now you can directly put the data, if the data is in Parquet format, to S3 tables. And then it acts as a managed data lake where you can interact with AWS services like Athena, Glue, QuickSight, SageMaker, or any third parties as well, whether it's Snowflake, Trino, Flink, etc. Along with that, you can also have an MCP server on the S3 tables, which can help you as an agentic kind of workload. So with MCP servers, you can just easily manage, like easily experiment and manage. So this is from one of my from one of my accounts in my testing. I just give a very like a very simple statement, which is like, okay, give me the highest revenue generator in 2024 and 5, based on one of my table bucket, which is daily sales in a single query. And it did help me to just create the table creation, the schema definition, and everything, giving me the highest review generators for it. So you can easily integrate MCP servers as well with S3 tables to get that data with just a simple query, as we were seeing there. The last part which I would really like to discuss is the Iceberg REST catalogs. So Robert did touch base upon it, but I just would like to say, think of catalogs or Iceberg catalog as an abstraction layer. They're just as an interface between your clients and your data stored in place. It decouples with clients, so you can use multiple clients in place, whether it's Trino, Flink, Spark, and it's an implementation for Apache Iceberg, basically exposing that particular API, which you can use with your applications as well. Now, with S3 tables, there are two types of IRC endpoints or REST Iceberg endpoints. First is called as a glue IRC endpoint, and the second is called as the S3 IRC endpoints. And I know I've been confused when it was launched, and I know customers have been, but I'm just going to give you a very simple reason why two exist. The first one is managed by AWS. That's an glue IRC endpoint. So you integrate with the glue catalog, and it will give you a direct integration with Lake Formation, SageMaker, any of that is, and it would be managed by AWS in itself there, right? Second is something, let's say if you want to have your own catalog and want to integrate or want to interact with Iceberg outside managing your own catalogs. That's where S3 IRC endpoints comes in place. You can manage the catalog and then integrate and access the S3 tables directly. So let's say if you're using Glue already, I would suggest make use of Glue IRC endpoints, because that makes that Amazon S3 or Amazon S3 tables would do the heavy lifting for you. However, if you have a use case like ClickHouse, because there was a bit of pieces which were missing in the integration with ClickHouse, and you want to manage your own catalogs, that's where you can make use of S3 IRC endpoints to interact with S3 tables and then work in the same way as you do with any Iceberg client as well, making S3 tables your data store and getting the benefit of the complete management and performance from there. Last but not the least, because this is a new feature, it's still developing, and you could see the momentum, how we have progressed with S3 tables. And that is going to stay. We do have few things planned as well, and it will go on. So this is a solution which I've built with other essays as well. It talks about how you can migrate your data from a general purpose bucket to S3 tables. The data can be either in Parquet format, Hive format, and it uses a serverless EMR Spark in order to move the data from your general purpose bucket to S3 tables. And that brings me to the end. Please feel free to use the QR code to give the feedback. Any feedback would be helpful. If you have any questions, I'm not sure if I have time, but yes.
Thank you very much, Prachi.
Thank you.
So you guys, plenty of time to network afterwards. I think we've got time for one question, if there's anybody in the crowd. I think everybody's feeling a bit tired at the end of this evening. Okay, well, feel free to come and find Prachi afterwards to ask some questions. And yeah, I hope you guys have had a lovely evening. So we do have to be out by 9 p.m., which gives you 40 minutes to enjoy yourselves, network, and get to know people around you. Thank you.